Hey physicists, we are going to go ahead and get some problems done today since we can't hang out together and whirl rubber stoppers over our heads. So I've got a couple of questions to work on with you, a couple of circular motion questions that I want to walk through with you, and then I'll also post a couple of problems for you to work on Canvas that we can discuss when we get back. I'm not intending for these to be super stressful, but they're kind of interesting questions. In all of the cases, we've talked about them kind of from a theoretical point of view, a conceptual point of view, but haven't actually applied numbers to them. And I wanted to do that today since we've got a little bit of flexibility time with our snow day. So the first question here has to do with driving a car around a corner. So we talked a little bit about this a couple of days ago, but like I said, didn't put numbers to it. So we're going to take a look at this question. Here we go. So it says a 2,000 kilogram car rounds a corner that has a radius of 45 meters. They're introducing the coefficient of friction again, and we'll be okay with that. We'll talk what that means in just a second. It says, what is the greatest speed that the car can have as it rounds the corner without skidding? So just like we've always done, if we're approaching a question that seems kind of scary, we're going to start out with our givens, right? So let's go ahead and write down our givens. We've got, and I would encourage you to go ahead and write this down with me so you've got it, okay? We've got a mass of 2,000 kilograms, and it says that it's going around a curve with a radius of 45 meters. It says that that coefficient of friction is 0.82, and it's been a little while since we've played with the coefficient of friction, so I just want to remind you that we said ages ago that the coefficient of friction is equal to mu times the normal force, or the force of the road pushing up on the car. So just an FYI, a reminder of that, okay? And then it says, what is the greatest speed, V max, that our car can go around the curve without skidding out, okay? So we talked a little bit about if you have you're going around a roundabout and it's icy, then the coefficient of friction goes down and then you're going to go in a straight line. It's actually true, and I hope that none of you experienced it, but it's actually true that if you go around a curve, even without ice, if you go too fast, then you won't be able to make the curve. So if we kind of think about this, draw a picture here. So here is our curve, okay, and here's our car. It's going in a straight line. That's the tangential speed, or the tangential velocity, okay? And it's going around this curve that's got a certain radius, and that radius was 45 meters. And we want to know how fast we can actually go. So we need to look at the forces that are acting. So if we look at the car from kind of a head-on perspective, we've got two forces that are acting. We've got the force of the earth on the car, that's Fg. And we've got the normal force, Fn, or the force, I should be a good physicist here and say that this is the force of the road on the car, and that's an Fn. We talked about last time that we were talking about these kind of questions that we've got the up and down forces, and those are equal, right? It's not accelerating up, it's not accelerating down, but then there's also a force that's pulling the car in, and that force is a frictional force, right? We talked about how the ice would minimize that force, and that's when we would slide out. So this is the force of the road on the car. This is the frictional force. Okay, so the frictional force is the force that's causing the circular motion. So when we write down our F net equation, oh, come on, stinker. There we go. F net, and this is kind of in that horizontal direction or in the plane of the circle. F net is going to equal the force of friction, and that force of friction is going to cause a centripetal acceleration. Okay, so that's kind of in that horizontal plane. We'll call that the X. We can also write an F net in the Y, and that is going to be our normal force and our gravitational force. And as we said, since it's not accelerating up and it's not accelerating down, those two forces have to be equal. All right, so I'm going back to the X equation, to this one over here. And the reason I'm going back to that is because that's where my velocity is. So force of friction, I'm just going to leave that as FF for now, is equal to the mass of the car times the acceleration, and it's a centripetal acceleration, so that's going to be VT squared over R. So just kind of like taking a step back to figure out where we're at and what we're doing. We are looking for V. That's our goal. That's what we're trying to figure out. We know the radius because the radius was given to us as 45 meters. We know the mass of the car. That's the 2,000 kilograms. Okay. And then we also need the force of friction. The force of friction, we said, was Fn times mu. Okay. Which is, so I'm just going to write this back out, mass of the car times Vt squared over R. I know mu. I was given that as 0.82. And I can figure out that normal force. And the way that I figure out that normal force is because I know that the force of gravity and the normal force have to be equal in magnitude, opposite in direction. So Fn, I'm just kind of bouncing over here, is going to be the mass of the car times the acceleration due to gravity. So that's going to be that 2,000 kilograms times 9.8 meters per second squared. Okay, I'm going to go ahead and do a little calculation here to figure out that value. Hold on just a second, get my calculator ready. So I've got 2,000 times 9.8, and I get 19,600 newtons for my normal force. Okay. Now I know my normal force, so I'm good to go. So I know my normal force, I know my coefficient of friction, the mass of the car, and I know the radius. So now it's just algebra, friends. You've got this. So here we go. We're gonna do some algebra to get our velocity all by itself. So I've got mu Fn. I'm going to multiply by r on both sides to get rid of this r down below the Vt. So I'm going to have an r on the top. And then I'm also going to divide by the mass of the car. And that leaves me with Vt squared. I want to undo the squared. To undo a squared, what do? Take the square root. And that, it's kind of an ugly expression that I've gotten written there, but that is how we're going to find the maximum velocity that we can move at. Why is it the maximum? Because, and I don't know if you remember this or not, but when we were talking about friction, just kind of a harkening back to way back in the day, when we were talking about the force of friction, that static friction, remember, it went up, 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 up. And so that frictional force is only going to be as high as it needs to be, but we're looking at that spot right there where it's at a maximum. Okay, so if the frictional force is at a maximum, we'll say maximum frictional force, then that means that we're going to have a maximum acceleration, which means we're going to have a maximum velocity. Okay, so we can go ahead and plug in our numbers here. We can say that Vmax is equal to the square root of, so that's going to be 0.82 times 19,600 newtons times the radius, which was 45 meters. And then we're going to divide that by the mass of the car, which is 2,000 kilograms. So you should do that. I'm going to go ahead and do that as well so that we can figure out what the value is. How fast can that car go around the curve and not skid out? So 0.82 times 19,600 times 45. I'm going to divide that by 2,000. And then I'm going to take the square root of that value. And I get a maximum speed, Vmax, of 19 meters per second, 19.016 if you want lots of sig figs, but I'm just going to go with 19. So hopefully that made sense. I'm going to go through another one. Again, or I guess I didn't say this before, but if that gets confusing, you can always go back, right? The beauty of video is that you can always go back and get another round of that if you want. So here's another question. This one's kind of a similar question. It says, a 1,000 kilogram car rounds a curve on a flat road with a radius of 50 meters and a speed of 50 kilometers per hour. Ooh, that's mean, right? Mean Miss Carveling. She added in a conversion. We'll do that in just a second. It says, will the car make the turn if the pavement is dry and the coefficient of static friction is 0.6? What about if it's 0.2? Let's take a look. All right, so similar question. We're going to start off as we did before with our givens. So we've got a mass of 1,000 kilograms, okay, a radius of 50 meters. It says that the speed is 50 kilometers per hour. And now we're going way back. I think this was the very first standard that we ever did together. So let's go ahead and do that conversion here real quick. So if we want to go from kilometers to meters, I'm going to have 1,000 meters in 1 kilometer. And going from hours to seconds, I'm going to have 1 hour is 3,600 seconds. Friendly reminder that that means that it's 1 hour is 60 minutes. 1 minute is 60 seconds. That's where I get the 3,600. And so then I can quickly convert here. Again, pulling up my calculator of 50 times 1,000 divided by 3,600 gives me a speed, a tangential speed of 13 point, I'm just going to write it as 13.9 meters per second. It's 13.88888888. So we'll just round to 13.9. Okay, that was fun. Little review in there. Will the car make the turn? Will the car make the turn if the pavement is dry and the coefficient of static friction is 0.6? So what does that mean? Will it make it? We don't usually ask that question, but let's figure it out. It's going to be the same setup in terms of our F-net equations as we had before. F-net in the x direction. The only thing that's keeping it in that circle is the frictional force. And the frictional force is causing a centripetal acceleration. Okay, so this is mu times Fn is equal to mv squared over r. And so really the game is, does the maximum velocity equal, or is it less than the maximum force? Is the force enough to keep it in that circle? So we can go ahead and do this. We just different ways. So we're going to remind ourselves too that we had that F net in the y direction is Fn plus Fg, which equals 0. So we know that the normal force has to be the opposite of the gravitational force. So that's going to be the mass times the acceleration due to gravity. 1,000 kilograms times 9.8 meters per second squared. Okay, I can do that one in my head. 9800, right? 1, 2, 3 newtons. All right. So if we've got 9,800 newtons, I guess one way we could figure this out that might be easier would be to just solve again for Vmax and see if our maximum velocity is less than what we can allow. So let's do that. So we've got mu Fn times r. We're doing the same algebra that we did the last time. Divided by m, square rooted gives us Vmax. So let's solve for Vmax. We've got, where are we at here? 0.6 times 9,800 newtons times a radius this time of 50 meters divided by a mass of 1,000 kilograms. And we want to find out what the maximum velocity is to safely go around that curve if the coefficient of friction is 0.6. So we've got 0.6 times 9,800 times 50 divided by 1,000. And then I'm going to take the square root of that. Oops, boom. And I get a maximum speed, a maximum allowable speed of 17.1 meters per second. Okay, so this is the maximum velocity possible on dry pavement. We look back to what the question said, and the question said that it was moving at 50 meters or kilometers per hour, which we figured out was 13.9 meters per second. So the 13.9 is below 17. So that means we're safe, right? We're only driving 13.9 meters per second. We can go up to 17.1 meters per second and stay safe. Okay, so that's part A. That one right there was part A. Now I want to do the same thing. I'm not going to do all the algebra again because it's the same question. We're just going to make the pavement icy. So now instead of doing the coefficient of friction as 0.6 in this round 2, I'm going to make the coefficient of friction 0.20. All of this icy stuff is very appropriate for the, reason that I get to make this video instead of talking to you about this in person. So here we go. So Vmax is equal to, it's going to be the square root. It's the same expression. It's the same one here. I'm just going to plug in my numbers. So I've got 0.2 times 9,800 times 50 meters divided by 1,000 kilograms. Okay, so it's the same problem, just a different coefficient of friction. And when we do that, let's go ahead. I'm just going to plug it all in one more time. So 0.2 times 9,800 times 50 divided by 1,000. Oops, I just cleared it out. That was silly of me. Let me do that again. Sorry. So we've got 0.2 times 9,800 times 50 divided by 1,000. And then I'm going to take the square root of that. And it says that the maximum speed that we can go on this icy road is 9.9 meters per second, 9.89. So don't push it, I guess is what I'm saying here. Vmax, the maximum speed that you're able to go on this icy surface is 9.9. It says that we're traveling 13.9 meters per second. That means, friends, that on the icy surface, if you were trying to drive 50 kilometers per hour, you would not make it around that curve. Okay? Hopefully that makes sense. I'm going to pause for a minute. I'll throw up a couple more videos in a minute with some other examples. Thanks, guys. Maybe. There we go. All right. Sorry about that. Change in plans. I was going to make separate videos, but I think this is easier. So hopefully those made sense. And now we'll take a look at a looping roller coaster. So this specific question is not about a looping roller coaster per se, but it's about this individual who I would not choose to do this. I just want to make that clear, but who would ride his bicycle down this big hill, converting potential to kinetic energy, as we know, and then go up this crazy loop and around and down. And people would, pay money to watch him do this ridiculous stunt, which is, all well and good. So Allo Daredevil Diavolo introduced a stunt of riding a bicycle in a loop, like I showed you the picture. Assuming that the loop is a circle, they're not actually circles. When you go on a looping roller coaster, it's a thing called a clothoid loop that's a little bit different to minimize the acceleration on your body so that you don't, black out, which is good. But anyway, we're gonna keep it simple here and assume that it's a circle with a radius of 2.7 meters. Okay, what is again the least speed he could have at the top of the loop if he's to remain in contact? So it's a similar question to the one about going around in the circle in the car, just a different application. So if we think about at the very top of the loop, okay. If we think about that, so here he is on his bicycle. Forces that are acting, it's always about those forces, right? You guys have gotten this. You've got the force of gravity pulling down, and you've got the force of the surface. The force of the surface pulls down as well, okay? So it's kind of funny. It's the net force acting on him in the the y direction is Fn plus Fg, and that plus is actually a plus this time because both of those forces are pointing downward. Those result in a centripetal acceleration, and we can mark that by m times a sub c. Okay, we're assuming there's no friction. We're assuming that all we've got there, because he's just barely going around, is the normal force times gravitational force, which equals m times a sub c. Now, we talked a little bit about how when I was whirling that yo-yo, if I go faster and faster and faster, then the tension force or the force that's pulling it back down would get higher and higher and higher. If you think about whirling something around in a circle, there's a a minimum speed that you can get so that the object actually goes all the way around. So if you go faster and faster and faster, this whole value is going to get bigger and bigger and bigger. Fg doesn't get bigger because remember, Fg is just m times g. The thing that would get bigger and bigger and bigger would be the normal force, okay? So the faster we go around the circle, the bigger the normal force would get. If I want to know the least speed or the minimum speed that we can go, I'm going to make the normal force go to 0. So that's when it would be going over the loop and just barely be touching the surface. Not a recommended choice, I just want to be clear, but it is there. So the minimum speed that we can go would be at a situation where the normal force is 0. So we can go ahead and solve this problem. I should probably write down some givens. I got ahead of myself. Sorry about that. So givens, what do we know? We know that the radius of the loop is 2.7 meters. And oh, that's all we know. That's kind of funny. We want to know the minimum speed that we need to go all the way around this loop. Now it's kind of a weird thing that we only know one thing. You might be saying, but we don't know his mass. You also might be saying, but I see a mass on the left side and on the right side. So let's take a look at what that means. So I've got m times g equals m times a sub c. Oh, look at that. See you later, mass. That's a nice thing because less so for Allo Daredevil Diavolo, but if you're going in on a loop-the-loop roller coaster, you don't want it to matter how much mass you have or how much mass is in the car, whether or not you're going to be able to stay in the car, right? That shouldn't be a thing. So that's good. So we've got the acceleration due to gravity is equal to vt squared over r. So now, really, friends, all you need to know, the only thing that matters to tell you the minimum speed is the radius of the loop. So we can say that Vt, this is the minimum now, is going to be equal to the square root of g times r. So I multiplied r to both sides to get rid of the r down here. And then I wanted to get rid of the squared. The way to get rid of a squared is to take the square root, right? So here we go. So Vt is equal to the square root of, so it's going to be 9.8 meters per second squared times the radius, which was 2.7 meters. And now we can figure out what that minimum speed, how fast does he have to be going there in order to make the loop. So 9.8 times 2.7, take the square root of that value, and you get 5.14 meters per second. So here, this would be a fun problem that would kind of combine some things. I'm not going to actually do the problem, but just to kind of get you thinking. If he has to be going 5.14 meters per second here, in order to maintain, so that's Vt, to maintain that loop, we could think about how high does he need to start, right? Potential energy to kinetic energy, you get what I'm saying here? We'd have to figure out how high he needs to start from rest in order to go with that tangential velocity up there. I'll just leave that for you to think about. It's kind of a fun question, but I'm not going to do that right now. All right, one more for you. Here it comes. This is the one that we were talking about yesterday. My fifth period class, we learned that Grace Crimmins is a silly silo aficionado and has been since she was, 4 months old or something like that, whatever it was. Anyway, thinking about the silly silo eventually, and remember we talked a couple days ago about how you stick to the wall. You don't really stick to the wall, but you experience some centripetal acceleration, and that is due to a frictional force. So we want to know the minimum speed. Again, we're talking about the minimum speed in order for us to stick, okay, that the cylinder and the rider have to be moving at so that when the floor drops, the rider doesn't fall. So let's think about this from a couple of different pieces of, or a couple different perspectives. So here is Grace on the silly silo, and this is while it's spinning and the floor is dropped out. So if we think about the forces acting on her, we've got the force of gravity, the force of the earth on Grace, Fg, right? And then the other thing that we said we had to have here, the thing that's holding her up, is a force of friction. So this is the force of the wall on Grace, the wall is acting parallel to, or the force is acting parallel to the wall, so that's got to be a frictional force, okay? And in order for her not to fall, we know that F net, this is in the y direction, has to equal 0, so FF has to be equal to the opposite of FG, okay? Now, this has nothing, there's no speed in this one. The thing we have to look at in order to talk about the speed is looking at it from the top-down view. So this is the side of, part of the silo, and here is Grace's head, and so it's spinning, spinning, spinning in that direction, and as it's doing that, because the wall's there, the wall is applying a force, isn't it? It's applying a force in towards the center. This is the force of the wall on Grace, okay? And that one is a normal force because it's applying a force perpendicular to the surface, okay? So we've got another F net equation. F net in the x direction is only the normal force. There's nothing else pulling or pushing on her, right? The only thing acting is pushing in, and that's equal to m times a sub c because it's a centripetal acceleration. She's going in a circle. So this is where the velocity is, right? That's where the velocity lives. So let's kind of work backwards here to figure out what's going on. New colors. All right, so we've got Fn is equal to the mass. So does the mass matter? We'll find that out. Times Vt squared over r, okay? We know, let's see, what do we know? I have been forgetting to write down givens, friends, and I apologize for that. Let me go ahead and do that now. So givens, I'm just going to put them up here so they're out of the way. We've got the coefficient of friction is 0.4, and the radius is 2.1, and it wants to know the minimum speed. Okay. All right. So we've got the thing we're looking for. We know the radius. Do we know her mass? Nope. Let's see if we need it. And then we've got the normal force. I don't know what the normal force is, but luckily I've got that other equation, right? I've got that other equation that says FF is equal to mu Fn. So right here, instead of FF, I'm going to throw in mu Fn. So I'm going to say mu Fn plus Fg is equal to 0, or I could just say that that's equal to the mass of Grace times the acceleration due to gravity. Now I'm getting somewhere because I've got an Fn here and I've got an Fn over there. I'm going to rewrite this Fn is equal to mg over mu, so I'm just dividing by mu on both sides, okay? And now we've got something we can use. Here we go. So m times g, the mass of Grace times the acceleration due to gravity, so that's her weight, divided by mu, is equal to the mass of Grace times Vt squared over r. Whew! Look at us. We got masses, they go away, all right? We can solve for Vt. So we can solve for Vt. How are we going to do that? Let's do that in some steps here. Multiply by r. Oh, it's just going to be one step. Look at us. R times g over mu is equal to Vt squared. Undo the squared by taking the square root. Okay. And there we are. We've got r. We've got mu. We know g, so we're in good shape. Let's go ahead and do it. Oh, there should not be a square root there because I already took the square root to get rid of that. Sorry about that. So here we go. It's going to be the square root of, the radius was 2.1. The acceleration due to gravity is 9.8 meters per second squared. Mu was 0.4. And this will tell us how fast that ride needs to be spinning in order for her not to fall. And in order for anyone else not to fall, because remember, it does not have anything to do with the mass of the person. So I'm just doing some math here, and I'm going to do a square root, and I feel like that might be wrong. I'm going to do that one more time. I don't trust what I was doing. I was typing while talking. That's a dangerous thing. 2.1 times 9.8 divided by 0.4 is, oh, that looks better to me. It's 9.8 divided by 0.4. Yeah, and I'm going to take the square root of that. Boom. We have to be going, it says, according to my calculation, if I messed up, I apologize, essentially 7.2 meters per second. Okay? So that means that anybody that's riding, as long as the thing is moving at 7.2 meters per second or more, will not slide down. All right? I hope you did okay working through those. I would not put something super hard on a quiz. We'll talk a little bit more about what that might look like once we're all back together in the class. But I'm going to add a sheet with a couple of problems on Canvas as well that I'd like you to work through. Following this stuff, I think you should be okay. Have a fantastic day, you guys. We'll see you tomorrow. Be well.